Hello everyone, welcome to a new chapter on electromagnetic waves. But before going directly into the waves, let us talk about a new topic which is called displacement current. The displacement current is a very essential thing from which actually we have got the idea of electromagnetic waves, and the person who is responsible for all this development is James Clerk Maxwell. All right. So in today's lecture, we will talk a little bit on displacement current, how it appears, and how exactly we came to the notion that there should be a current named as displacement current, although the name was coined by James Clerk Maxwell himself, but it was a current which was missing in one of the law or the one of the fundamental laws of electromagnetic waves. So we will come to the discussion on all of these things. Let us start with the fundamental laws of electromagnetism. Now, if you talk about the laws of mechanics, in that case, we know that Newton's laws are very important and that can be treated as the fundamental law. So, there are always some fundamental laws in a particular discipline which actually governs the evolution of that particular discipline. So, if you come down to the field of electromagnetism or electrodynamics, in that case, there are four laws which are never violated and which proves to be the pillars, or I can say the four pillars of the building of electromagnetism. So collectively these laws are known as the Maxwell's equation, although the laws individually are different. For example, you can see the four different laws which are shown in integral forms. For example, this one, this one, this one, and this one. The first of which is known as the Gauss's law for electricity or Gauss's law of electrostatics. The second law is known as the Gauss's law of magnetism. Then, following which, we have got the Faraday's law, and ultimately we have got Ampere Maxwell's law. Now, the first law is Gauss's law of electricity, which means that the electric flux out of a closed surface is equal to the total charge enclosed by the surface divided by epsilon naught. Now, that is what is a Gauss's law in electrostatics, we all know. Now, come to the Gauss's law of magnetism. Suppose you have got the total magnetic flux coming out of a surface, closed surface by the way, that is why the integration sign has got a small circle here. Small circle in the sense this is an area integral by the way. B dot dA means dA is a small elementary area. So this is an area integral. Now, if the area closes on itself, for example, consider the football surface, it closes on itself. So that is why the surface is closed. And if you have a closed surface, what you create is a volume inside. Got it? So in football, we have a volume which has been closed by a surface. So that is why this is a closed surface integral. Okay. Many a times we would like to write an S sometime somewhere here. So for example, here, here. Now S signifies the surface integral. All right. So E dot dA is equal to Q upon epsilon naught, where Q is the total charge enclosed by the surface. Similarly, since you do not have any magnetic charge or you do not have any magnetic monopole to be existing, so that is why total flux out of the closed volume of magnetic flux out of the closed volume is equal to 0. Now come to the Faraday's law. In Faraday's law, what we get that EMF induced is equal to the minus d phi b upon dt. Suppose you have got a closed loop, one single loop, and if there is a change of magnetic flux through that loop or linked with that loop, in that case there will be an EMF induced, and that EMF is given by the minus d phi b upon dt, rate of change of the magnetic flux. All right. Now comes a very important law, which is the Ampere Maxwell law. But the thing is that this law was initially put forwarded only up to this, only up to this, and up to this it is known as the Ampere circuital law. All right, you will come to know about it whenever we will see the magnetostatics or magnetic effects of current. In that particular chapter, you will come to know about this Ampere's circuital law. But here, I mean, Maxwell noticed that this law has got some kind of a problem. All right, we will come to that. And he modified the law and introduced a new term. All right. So in this particular law, the first current that you see IC That is what is a conduction current. Conduction current means the real current. Okay, the current which is actually flowing through a conductor. And this particular current is known as the displacement current. That means that's a newly introduced current to this particular uh, law, and that is why we can say that Maxwell has modified this particular thing. Now let's come to the detailed discussion on Ampere circuital law. What it states that the line integral of magnetic field around any closed loop is equal to mu naught times the net current I flowing through the area enclosed by the loop. Now, what actually it means is that suppose you have got a straight conductor. This is a conductor. If current I is flowing through this conductor, and you point your thumb towards the direction of the current and curl the fingers. In that case, the curling of the fingers will give you the direction of the magnetic field. So that means if this is the conductor which is carrying current I in the upward direction, then there will be a magnetic field like this. It will encircle the conductor in this fashion. There will be a lot more circles actually. Magnetic field will keep on encircling this magnetic field. I have although shown only two circles. Got it? So magnetic field at any point will, because of this current, okay, can be obtained. And the circulation of the magnetic field basically is given by the line integral. Now this is not a surface integral because I have dl. L means small line integral. Line integral means dl is a small elementary length, because suppose from here to here is a dl or delta L, which you can see over here. So if you take summation of all such delta L's, then you will get the circumference of this circle. So that is why the magnetic field circulation is given by the line integral, by the closed loop line integral dot dl b dot dl, that's equal to mu naught I. What is mu naught? Is the absolute permeability of free space, whose value is given by 4 pi into 10 to the power minus 7 Henry per meter. Now the thing is that at any point on that particular circle, suppose you are considering either the inner circle or outer circle, because there will be lot many circles here. At any point on any circle, the magnetic field is given by the tangent to that point. Suppose here you want to find the magnetic field. Now let's consider this is the conduction current IC, which is coming out of the plane of this paper. That means straight away towards you it is coming up. In that case, at this point the magnetic field will be given by the tangent drawn at this point. Similarly, at this point, magnetic field will be given by the tangent drawn at this point. So if you just give me any other point, so for example you talk about this particular point, what will be the magnetic field here? It will nothing but the tangent along this line. Similarly here it will be tangent along this line. So it is just like the tangent drawn all over the circle will give the magnetic field at that point. All right. Okay, but this Ampere circuital law is not consistent. That's the major thing. People, until Maxwell came into this discovery, people started believing at Ampere circuital law blindly. And there was no point also, because the discovery of displacement current is not so easy in a sense to say, or it's not a common sense kind of a thing that you infer that okay, this is a missing term and this should have been there. Actually that is not the case, because it looks complete and there is not a situation where this Ampere circuital law was proven to be failed. But there is a situation where actually you cannot apply Maxwell's Ampere circuital law. All right. So I will talk about that physical situation, although there are mathematical deviations also. But to prove the mathematical deviations, I have to talk about something else like divergence, gradients, curls, etc. Those terms you have not encountered till now. So that is why we shall talk about only a physical situation where we will talk about the charging of a capacitor. So let's come to the next slide. So in this slide, we will try to understand how a capacitor charges and how in this problem, if we apply the Ampere circuital law, it fails. Okay. So look at this problem very carefully. This is a capacitor. This is a one plate of the capacitor. This is another plate. And here is a battery connected. Now this is the positive terminal of the battery. That's the negative terminal of the battery. So naturally, since this is positive terminal, so this plate will be positively charged and this plate will be negatively charged. So if I have to put the charges, this plate will be positively charged, this plate will be negatively charged. Okay, because why? This is connected to the negative end of the battery, this is connected to the positive end of the battery. All right. Now what? This charging of the capacitor, it occurs for a certain amount of time. I mean, like, suppose you have connected this battery for some second, it could be a nanosecond, it could be a microsecond of time, but very small, of course. It doesn't take much time, but for a small duration of time, there will be charges which will keep on accumulating on this particular plates. That means as soon as you connect the battery, all the charges together doesn't go to these particular plates, as you can see in this particular thing. The charges will flow through the battery. I mean, that is the reason why it will take some amount of time to get these plates to be fully charged. That means where there is no more charges to be accumulated. That is a state of the capacitor where the capacitor is said to be fully charged. All right. But to get fully charged, the capacitor requires some amount of time. All right. In that particular time, the current changes. The current then doesn't become a steady factor. That means time independent factor, it doesn't become. It becomes a function of time. So basically what I should write here, actually, I should write this current to be some function of time. All right. So this is a time dependent current which is flowing through this circuit. Okay, remember the time required to be fully charged, full charge of the capacitor will be very small, of the order of nanosecond or microsecond, maybe picosecond in some cases, but it is a definite time. There is a time gap. So within that time the current will change with time. That means either current will increase or basically current will say increase with time till that phase, and it will sharply drop down once the capacitor is fully charged, because there will be, if the capacitor is fully charged, then the potential difference across this battery and across the capacitor will become equal, and there will be no current flowing through this circuit. Okay, so when the capacitor is fully charged, there is no current. Current will flow only when the capacitor is getting charges or when the capacitor is charging. All right, so I hope we have understood the charging of a capacitor. Now let us try to understand how we can apply the Ampere circuital law. Now suppose I want to find, because current is flowing through these wires, these are wires, so through this wire current is flowing in this particular direction. So because of that current, if I want to find the magnetic field at a point P at some amount of time t, say for example, then I have to construct an Amperian loop. All right, considering that point within the loop. So what I do, I have constructed an Amperian loop like this. This is my loop, because I know that from my previous discussion in the previous slide, that if there is a steady uh, current, say for example steady wire, this is a steady wire, this is a wire which is carrying steady current I, the magnetic field will come up like this symmetrically. Okay, although my diagram may not be that symmetric, but this loop should be symmetric, as if its center is somewhere here. So similarly here also there should be a loop, and at any point on this loop, if you want to find the magnetic field, I told what, that you have to draw a tangent, but that tangent will give you the direction of the magnetic field. What about the value? What about the magnitude of the magnetic field? That can be obtained from the Ampere circuital law, which is given by B dot dl integration equal to mu naught times the current which is being flown in the steady, the current which is being flown in the conductor. So in this case, corresponding to this Amperian loop, this loop is by the way known as the Amperian loop. Okay, so corresponding to this Amperian loop, there are two surfaces you can construct. One is this surface whose bounding line is this. Again, you can consider a pot-like surface. For example, this particular surface I am talking about, whose opening line is also the same Amperian loop. So corresponding to the same Amperian loop, you have two surfaces. One is the top surface S1, another is the surface S2, which is a pot-like surface. Okay. Now, for the surface S1, that means this particular surface, if I have to consider, then what I observe is that this current lead or the current wire directly passes through this surface. That means surface fall in between the current line. So that is why I can easily say that there is a current I or IC. IC means the conduction current, C for conduction, which is passing through the surface. So that is why what Ampere circuital law should give me, that line integral of magnetic field is equal to mu naught times the conduction current. That's pretty well. Means for this particular surface, I can easily apply the Ampere circuital law. But if I have to consider the second surface, for example, this S2 I am talking about, for this particular surface, this surface is not bounding any current, because see, the current lead comes and ends at this plate and the surface comes through in between the plates. All right, so the bottom of the surface is somewhere in between the plates. So that is, the current is not passing through the surface, and this is an open end. For this particular surface S2, this is an open end. This is just like if you have a pot and you have cut it in between. So the opening of the pot is this and the bottom of the pot is this. So that is why, since current is not flowing through the surface, I cannot say that surface is holding a current, because current is not piercing or current is not passing through the surface. So that is the reason why there is no conduction current through the surface. So for this surface, I should get Ampere circuital law as line integral of B dot dl to be equal to 0, because on the right hand side I have mu naught into IC, the conduction current. But in this case, since the surface is not holding up any current, that conduction current will be 0. But for the same Amperian loop, the Ampere circuital law is giving me line integral of B dot dl to be equal to 0. Now here is an inconsistency. That's an observed inconsistency and practical inconsistency. And to a practical problem, this is not an hypothetical problem. Why practical problem? It's because we are considering the same Amperian loop for the charging of a capacitor, and I want to find the magnetic field at a point P, but corresponding to the two surfaces S1 and S2, S1 was giving me a different form of Ampere circuital law, but considering S2, it gives me a different form of Ampere circuital law. Left hand side remains same for both these surfaces, that is in line integral of B dot dl, that remains the same, but the right hand side of the equation is 0 for the surface S2 and is equal to mu naught into IC for the surface S1. So this cannot happen. If you have a law, law means what? That's the rule which governs a particular nature, a particular behavior. So the law cannot behave in two different circumstances differently. For example, if you have a law uh, framed everywhere to be valid in this country, then that cannot be different in one part of the country and in another part of the country. That's not it. The law has to be uniform. So if Ampere circuital law is to guide the generation of a magnetic field because of a flowing current, then it should give the same thing for any kind of surfaces. Got it? It cannot behave differently for different kind of surfaces. But here we have observed that Ampere circuital law was behaving like differently. So that is something which has been observed by James Clerk Maxwell, and he said that there should be something which is missing in the Ampere circuital law. And what is that missing link? What is that missing term? Let us find out in the next slide. Now here you can see, let us now carefully observe what is passing through the surface S2. Okay, fine. I understand there is no current passing through the surface S2, but is there something which is passing through S2? Yes, the answer is yes, and it is the electric field which is changing with time, and the lines of force are passing through the surface S2. For example, as already I told that whenever this is positively, this particular plate is connected to the positive end of the battery, this plate is connected to the negative end of the battery, this plate becomes positively charged, this plate becomes negatively charged. But the plates do not become instantaneously fully charged. Suppose at time t equal to 0, one positive charge come here, one negative charge come here. Then what you get? You get an electric line of force from positive charge to the negative charge. So that's the electric field. Similarly, in the next instant of time, suppose another plus charge come here, another minus charge come here. So you get one more electric field line. Then again in the next instance, there is one pair of charges which appear and you get another electric field line. So what you see through this surface, these electric lines of forces are passing. All right. And it is changing with time because electric field is changing with time, because at time t equal to 0 there was only two charges plus and minus. Then in the next instant another pair appeared, then again another pair appeared. So like that until it becomes fully charged, the charges will keep on coming onto the plates. So that is why this electric field is not a constant electric field, but it varies with time. So you get a term like this. Okay, this field will vary with time. Now if the plates have the total area A and total charge Q, then the electric field in magnitude is given by Q upon A epsilon. How exactly we get that? We get it from the Gauss's law itself. What Gauss's law said? That integration closed surface integral E dot dA, that's equal to Q by epsilon naught. So if E is constant, when E will become constant? E will become constant when the capacitor is fully charged, because then there will be no variation of electric field. So in that case you can consider that electric field to come outside. This is the total area which is given by Q by epsilon naught. Integration dA means the total area A, Q by epsilon naught, or it implies E to be equal to Q upon A epsilon naught. Okay, that is what you get the value of the electric field when the capacitors are fully charged, capacitor plates are fully charged. All right, so that's what you get. Then in that case what will be the flux of electric field? Now we know flux of electric field is given by nothing but product of the electric field multiplied by the total area. So if you just put it multiplied by the area gets cancelled, you remain with Q by epsilon naught. Now if you derive this, derive with respect to time, in that case you can write d phi E upon dt. Phi E I have written here because that's an electric flux, not a magnetic flux. Had this been magnetic flux, I would have written phi B, but here I have written phi E. So d phi E upon dt, that's equal to 1 upon epsilon naught dq dt. Because epsilon naught is a constant, you cannot derive with respect to time. So what you can derive is q. So that is why the rate of change of charge accumulation on the plate with time is equal to epsilon naught will come this side. So epsilon naught times the rate of change of electric flux across the plates. So that's what I have written over here, that dq dt is equal to I, because we know rate of flow of charges or rate of change of charge with respect to time is some kind of a current. What current I have not said it yet, but it is some kind of a current which is given by epsilon naught times d phi dt, the rate of change of uh, electric flux. Let me rub this part. Right. So this particular current is known as the displacement current. Okay, this is a newly introduced current which we call displacement current. Got it? So that is how the Ampere circuited law actually became complete now. So that is the reason why if you have to write the Ampere circuited law, now how you will write it? You will write it as line integral B dot dl, that will be equal to mu naught times the conduction current which was originally proposed by Ampere plus the contribution which will come from the displacement current, that is why mu naught epsilon naught d phi E upon dt. Okay, this is a new form of law, you can say. That is why, because Maxwell modified it, so that is why we call it the Ampere Maxwell's law. Okay, so you can get this in the first slide where I showed those four fundamental law. The last of those, that particular law, is known as the Ampere Maxwell law. So that is how we have generated the displacement current. In brief, sometime people like to write it as equal to mu naught IC plus mu naught I D. D means the displacement current. Got it? Which is equal to epsilon naught times d phi upon dt. All right. So that's all about the generation of displacement current. In the next lecture, we shall understand how this displacement current is important, or how the understanding of displacement current is important for the understanding of the generation of electromagnetic waves, because it came with the understanding of light, because people didn't understand what is actually the light. Later on, Maxwell claimed that light is nothing but an electromagnetic wave where both the electric field and the magnetic field oscillates. But the thing is that in the space, whenever suppose the light is coming from sun to earth, then in between you do not have a conducting medium. There is no conducting medium such as iron or any conductor like that. But how come then there is a electric field which is oscillating? And if there is an oscillating electric field, or if there is a current, in that case, how exactly, because of that current, magnetic field is induced? Because otherwise the magnetic field will not induced. But it is only because of the oscillating electric field the magnetic field is getting induced. So magnetic field, as Ampere said that magnetic field can be generated only by the conduction current. Then Maxwell came and said, no, this cannot be the case. Magnetic field can also be generated by a time varying electric field or time changing electric field, because in the space you do not have a conduction current, but even then you get an oscillating magnetic field. So there must be something which is responsible for that generation, and what is that? It is the time varying electric field. So in the next class we shall understand the very detailed nature of the electromagnetic field or electromagnetic nature of light. All right. Along with that, we shall discuss the electromagnetic spectrum, where you have gamma rays, X rays, down to the radio waves in the increasing trend of wavelength. Those things we will discuss in the next class. Okay. So for today, this much was there. Please go through this very carefully. Thank you.